Hi, myself Naveen Kumar Saini. In the course Antenna and Wave Propagation, today we are going to discuss about the Ampere's circuital law, and that is which gives the Maxwell's equation. So what is the Ampere's circuital law? So here the Ampere's circuital law is representing that the line integral of H around a closed path is equal to the current traversing the surface bounded by that path. Okay. So how it is represented? It is represented as H dot dl is equal to I enclose. What it is represent that when we have any concurrent conductor, and if we want to find what is the electric field at some point away from this concurrent conductor, right? So what we do, we simply use this formula H dot dl is equal to I enclose, and when it is the closed surface, closed path, so it is representing that this point we enclose this concurrent conductor. So this is the one example where we are using the concurrent conductor. It may be any the current sheet or the current volume. Okay. So by using this Ampere's circuital law, we can find the value of H or the magnetic field intensity. So this is another method, and just like if we have the current distribution which is uniform in nature or symmetrical, so for that purpose we use the Ampere's circuital law. Otherwise we can simply use the Biot-Savart's law for finding the magnetic field intensity. So now we will try to find one of the Maxwell equation from this Ampere's circuital law. So H dot dl is equal to I enclose. So we will apply the Stokes theorem. And we know the Stokes theorem, which Stokes theorem relate the closed path to the open surface. If we write this Stokes theorem, so in this way, how we can write it? We can write it as the H dot dl is equal to H cross H open surface into ds. Okay, so this relates the closed path that is equivalent to the open surface, and this is nothing but the I enclose. So in this way, when we apply this one and we put this value in the left hand side, so what will happen? So before that, we must know about the I enclose, that is nothing but this is a J dot ds. The current density passing through the surface is also equivalent to the current enclose. So when we compare these two equations from here, if we are getting this H dot dl is equal to del cross H into ds. So when we put this one into this equation and I is J dot dl, then when after comparison we will get the del cross H is equal to J. So this is the this equation represent the magnetostatic field is not conservative in nature. So we know the condition for the conservation. So in the conservation condition is what? That the curl of any vector is equal to, if it is 0, right? So if it is 0, then this is the case of conservation. Okay. But if it is not 0, then in this case it will be the non-conservative nature of any vector field. Okay. So here we cannot write del cross H because it is always equal to J. So if in place of H we are taking the only any vector, right? So if we write the del cross A is equal to 0, then it will be 0. Then in that case it is conservative in nature. So here del cross H is J. So this is a Maxwell's equation for the magnetostatics. Okay, so this is a description about the H dot dl. So this is representing here that this equation holds regardless of whether the current distribution is symmetrical or otherwise. H can be determined by using this expression only if the symmetrical current distribution exists. Okay, so some examples for this using Ampere's circuital law is the infinite line current, infinite sheet of current, and the infinitely long coaxial transmission line. Okay, so for finding the value of H, we will use this Ampere's circuital law, and we will apply this into the above examples. So in this case, what is the main important point which we have to take care before solving this type of problems? H dot dl both must be parallel to each other. If H dot dl is H and DL is parallel to each other, then it will give the I enclosed. It will be give the some value, right? If H or DL both are perpendicular to each other, in this case this value will become 0. Okay, so the case which we will take it, that the direction of H and direction of DL must be same direction. So for that, to implement all these concepts which we have just discussed, we will take one of the example or the one of the application of the Ampere's circuital law. This is the infinite line current. So the case of this infinite line current, what we are taking one of the line current in which the current I is flowing into this, right? So current is flowing into this, and we want to find the value of H at the point P. So for this case, what we will do, we will enclose this current carrying conductor, right? If we enclose this current carrying conductor, so in this, that is why we are taking this path. So this path is nothing but this is the Ampere'S Ampere'S path, okay, which enclose this current carrying conductor. So what we want to find the value of H. So what we will do, we will take one of the element through this path, that is the in this way we are taking this element and we are taking this DL along this path. Okay, so what we will do, we will take the H and DL, both must be in the same direction, right, as we said before. So if we take the cylindrical coordinate system for this particular element, so in that in this case this distance from this point to this point will be rho. This is rho and this is also rho. This is the radius of the cylinder, right? Or in this case we can say this is the radii of the path, so closed path. So when we apply this Ampere's circuital law, H dot DL is equal to I. So what is the direction of DL? DL direction is tangent to this one. So what is this direction? This is the phi direction, right? This is the A phi direction. Because we know in cylindrical coordinate system we have one is the A rho, A phi and A z. So these three unit vectors are perpendicular to each other. Okay, so if we take phi, A phi, so it means if I am writing the H phi for this case, so it means DL must be in the same direction. Okay, means this element must be of the same direction, that is A phi. So for that multiplication we will take the H phi into A phi. So in this way, this A phi and this A phi, what is this value? A phi dot A phi, this value will be 1. Okay, so this same concept we have applied here, that in this way we will take the A phi dot A phi, that is the 1. So from where we are getting this DL. So in this way we can see that DL is what? DL is this one, right? So this is the rho, this angle will be your D phi. Okay, so that is why this DL will be equal to what? This DL will be equal to rho D phi. Okay, so when we write it in terms of the vector, because this is the magnitude, if I am writing in terms of vector, so in this vector this will be equal to rho D phi A phi. So same concept we will apply in every problem. So here we can see that in place of DL we can write the rho D phi into A phi, and here the component of H is in the direction of phi as well. So we can take the H phi A phi into rho D phi into A phi. So that is why A phi dot A phi will be 1. Then the current will be equal to I is equal to H phi integration rho D phi. So because this, for this particular point P or for this Ampere'S path, the value of rho will be constant, so we can take it outside. But the range of phi from this point to this point, this will be what? This will be 2 pi. So the minimum value of phi is 0 and the maximum value of phi is 2 pi. So when we integrate this with respect to 0 to 2 pi with respect to phi, so this value will be 2 pi into rho. So H phi will be what? H phi in this case will be, because H phi is a component of the vector H, so H phi we can write the I divided by 2 pi rho. So this is the component. So if I want to write in terms of the vector, So in terms of vector, I can write it because h phi. So phi is the direction of the vector h. So here we can write the h is equal to I upon 2 pi rho into a phi. Okay. So I think this point is clear how we can find the value of h for the infinite line current. Now come to the second of the application of Ampere's circular law. The second application is by using the infinite sheet of current. So for that thing, what we are taking, just like in the previous case, we have taken the one of the current carrying conductor, right? Now we are taking the multiple current carrying conductor, we are putting onto the one sheet. So in this way, this sheet, this is the one of the sheet which is nothing but is an infinite sheet, right? So this infinite sheet is there in which the infinite current carrying conductors are placed onto this one. So direction of current carrying conductor in the previous case was in the z direction. Here the direction of current carrying conductor is towards the y direction. Okay. So it means there is a density of the current carrying conductor onto this sheet. So that density or the current sheet density is represented as the K. Okay. So this is representing as the K. So as the K is in the direction of y, so we can write K is equal to Ky into Ay. So Ay is representing in the direction of y. So this is a complete current density which is lying onto the sheet, infinite sheet. So now what is our question? Our question is how to find the value of h at a point here. Okay. Maybe here or maybe here. So what we will do? Again we will draw the Ampere'S path. So for this particular sheet, the Ampere'S path will be like this. So it will crossing this complete sheet, right? So 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So this complete closed path or Ampere'S path is closing this infinite sheet. So one element we have taken, right? So now our question is how to find the value of h for 1 to 2, 2 to 3, 3 to 4, 4 to 1. Because if we found the value of h by using this Ampere's circular law, and if we know the dl, then simply we can take a dot product and we can find the value of h. Okay. So now before going into the detail of this for this diagram calculation, so what we will take this sheet current density which is the Ky. So the unit for this current density is what? This is the ampere per meter. Okay. So this is nothing but the K. Now what I want the current. So in this case current will be what? This current will be equal to the this will the sheet current density into the distance or the width. Okay. So in this way I current is I enclose, that is equal to the sheet current density that is in the direction of y. So it will be Ky, and the width. So what is this width? Width is that width which is through which across this width the current carrying conductors are lying. Okay. So we can see that this density is towards the y direction, and at which width it is crossing? It is crossing the B, right? 2 to 3 or 4 to 1. So this width is the B. So that is why we can write the Ky into B. Okay. So this is the current. This is the value of current enclosed. Now our question is now how to find the value of H. So for that one, what we will do? We will take the element from this sheet or the 2 points from this sheet. When you are looking from this side, so what we will see? We will see, you can take it as the 1, this is take it as a 2, and here again I am taking as the 1 element, and this is the element number 2. So if we are holding the current carrying conductor like this, so it means what is direction of H? Direction of H will be like this one, towards the finger. Okay. So in this way the direction of current will be H will be like this. Similarly, when we are holding this current carrying conductor in this direction, so what is direction of H? Direction of H will be across this fingers. So it will again be like this one. So this is the direction of H. Now we can see that this is the point at which these two lines are crossing to each other. So if you are taking this first for element number 1, this is the H1. For element number 2, this is the H2. Where so at this particular point, when we take the direction of H1, so direction of H1 will be like this one. And the same point at this point, because of this second element, direction of H2 will be like this. Okay. So if I are taking the element, so we can write it as a DH1, and for the element 2, we can take it as the DH1 for this and DH2 for this one. So DH1 and DH2, so the resultant of this one will be what? This will be nothing but this will be DH. Okay. And here we can see this is the axis. So this axis is Z greater than 0. This one is Z less than 0. So this one is Z greater than 0. This one is Z less than 0. So similarly, at this point, this is the DH1. So at this point, DH1 will be like this, and this is the second element due to second element. So this will be your DH2. So the resultant between DH1 and DH2 will be this one. So this is again DH. So by this you can see that when for Z greater than 0, the direction of DH will be what? If you are looking for this case, then DH1 direction will be towards AX. For Z less than 0, this DH direction will be minus of AX. Okay. So by this you can see for this element, right? So towards above the Z greater than 0, above the Z greater than 0, what we are finding? We are finding the 4 to 1. Okay. So this is the direction of X, positive X. So this will be nothing but the DH, 4 to 1, right? And when we go down 2 to 3, so we see this again the DH, which is in the direction of AX, minus AX. And what about this 1 to 2 and 3 to 4? So when we take it as like this, this is your, you can take it as the 4 to 1. So 1, 2, 3 and 4. So this direction, so you can take it as the Z greater than is this one. So you can take from here 1, 2, 3 and 4. So this one 4 to 1 will be what? This will be above the Z greater than 0. And from 2 to this 2 to 3, this will be Z less than, or you can say Z less than 0. And in this case, the direction of H will be minus of X direction. Okay. So now this concept we will apply in this case by using this equation H dot dl. See, 1 to 2. So what is the 1 to 2? 1 to 2 H value of H is 0 and 3 to 4 value of H is again 0. But 4 to 1 and 2 to 3, the value of H is greater than H is plus AX and minus AX. So we see here Z greater than 0, the value of H is we are taking as the H naught in the direction of X. Z less than 0, we are taking minus H naught in the direction of plus X, right? So when we apply this, so we see that 1 to 2 and 3 to 4, the value of H is 0, and 4 to 1, this is a positive H naught, and this is 2 to 3 minus H naught, right? So when we apply this, then in this case, what we are getting H dot dl, that is equal to 2 H naught into B, right? Because this will become 0, this will become 0. So these two will left, and we combine this, then the value will be H naught into B, that is 2 H naught into B. So what we are doing now, we are just putting all together. In this case, this will be equal to the KY into B. This is I enclose. I enclose. So in this way, what we found? We found the value of H naught. H naught will be what? H naught B will be cancelled out. So H naught will be KY by 2. So by this, we can write the H naught is equal to KY by 2. So we are just simply writing in place of H naught as a KY by 2, and Again we are applying putting this value h naught ky by 2 into this term, then it will become minus 1 by 2 ky into ax. Okay, so this is z less than 0. So by this way we can find the value of h, that is z greater than 0 and z less than 0. So these two values depends for the current density, sheet current density, that is the ky. Okay, so in the plus x direction and the minus x direction. So if we want in general form of the infinite sheet of current density k, then we can write h is equal to 1 by 2 k into an. Okay, so this k into an. So what is the value of h? H will be the perpendicular to the k and an direction, right? So an is a unit normal vector which is directed from the current sheet to the point of interest at which we want to find the value of h. So this is the way how we can calculate the value of h. Similarly, we can apply this concept of Ampere's circular law for infinitely long coaxial transmission line, in which the question is how to find the value of h everywhere across this coaxial transmission line. So it means what we required, we have to find the Amperean path. So for this one, suppose we have this inner conductor and outside we have this outer conductor. So what is the value of h everywhere? So what we will do, we will take the Amperean path. So what are possible Amperean paths? First is inside this conductor. This is the L1 which is representing like this. Second Amperean path will be in this way. This is the L2. So we can see second Amperean path. Third one is the L3 which is through this outer conductor. So this is the L3. Then last one is the outside this coaxial transmission line, that is the L4, right? So L4 is representing like this one. So here we see that for the inner conductor, for this inner conductor, the current is flowing outside this board. We are representing as the I outside the board. And to complete the circuit or the closed circuit, we are taking the I inside the board. That is the minus I current which is flowing inside the board in the outer conductor. So now we will apply the H dot dl is equal to I enclosed or the Ampere's circular law into this case. So this possible paths which is crossing this coaxial transmission line are the 4. So what is the ranges for this transmission line paths? For the L1 we will take from this point 0 to A, because inner conductor is of radius A and the outer conductor's inner portion is B, and the width of this conductor is T, and again last one we will calculate for the greater than B plus T. So when we take this one as a cylindrical coordinate system, so we are taking the rho as the variable. So rho will be what? Rho will be less than A, right? So this is the first Amperean path. Second one we will take the rho A to B, because this one is the A and this one is the B. So in between that we will take the L2 path. Third one is rho that is greater than B and less than equal to B plus T. So in this path, for this path we will take the value of rho as the between B and B plus T. So between these two lines, these two circles, we will take the value of H. Last one is rho which is greater than B plus T. So this is the B up to here and this one is the T. So total length from here to here will be what? B plus T. Okay. So L2 will be greater than B plus T. So in this way, we will take the regions for finding the value of H by using the Ampere's circular law. So infinitely long coaxial transmission line. So just simply apply this concept of H dot dl is equal to J. So by this we can find the value of H here. that will be h phi is equal to I rho upon 2 pi a square. Similarly, we can find for the a to b. So for this case, h phi will be equal to I upon 2 pi rho. And third case will be between the b to b plus t. So for that, it will enclose the current I and the density j. So this will be j dot ds. So by this, the value of h phi will be equal to this much I upon 2 pi rho 1 minus rho square minus p square upon t square plus 2bt. So when we combine all this all together, then the value of rho or the h will be based on the value of rho. So when it is 0 to a, then there is a linear graph from 0 to a, where the value maximum value of h will be I upon 2 pi a. Okay, so we can also see it here. So h phi, this h phi is variable. This h phi is directly proportional to the rho. Okay, so the linear relation, and here in the second case h phi is inversely proportional to the rho. So in this way, it will reduce in the area from a to b. Then we have the rho h that is equal to I upon 2 pi rho, and but here is the one factor, that is a rho square, right? So it will be have to be considered for drawing this this graph between the b, that is b to b plus t. So if we see 0 to a, there is a linear relation between that one, and a to b, there is an inversely reduced value of h phi, and greater than b and less than b plus t, again it will reduce, and after b plus t, so this value will be 0. Why it is 0? Because for the inner conductor, current is flowing, that is plus I, but for the outer conductor, the current is flowing as the minus I. So when we want to find the value of h outside this complete conductor, so this complete conductor value h phi will be into dl will be what? That is the I enclosed. So total I enclosed will be what? This will be plus I and the minus I. So this value will be 0. So that is why after the b plus t, the value of h will be equal to 0. So these are the three applications which we have discussed right now. First one is the infinite line current, second one is the sheet current, and third one is the coaxial transmission line. So I hope you understood these applications of Ampere's circuital law. So these are the book which we have followed about the MNO Sudoku, and the reference book is the HIT. Thank you very much.